ready to be dealing with the final session of the day. And we're starting off, so we're going to be hearing about epidemics and diseases. We're starting off with my colleague, Valerie Isham, who's going to be talking about epidemic models and networks and informing health policy. Thank you.
Thanks. So the title I was given was the informing health policy bit. But I work with epidemic models, so this seems a natural thing. But I should emphasize that I'll talk about the models as if it's infection, because we're informing health policy. But these sorts of models are used a lot for the flow of information across a network, processes in general, particularly rumors, information, and that sort of thing. So it's worth bearing in mind that they would apply, they're used for viral marketing, for example, so relevant to the sort of thing that Giles was talking about this morning. So what I'll talk about is say something about purposes of modelling, some simple models, what we can get out of those, why we use stochastic models when we do, and then how we generalise the state space, so the population structure, so that we think about, that's where the networks come in basically, and what the challenges are to thinking about transmission dynamics on networks. Okay, so the purposes of modelling, from my perspective at least, are that if we can understand the dynamics, we can open up the possibility of controlling the spread of infection. We're interested in things like, how do we detect a new outbreak of an existing disease, or how do we detect the emergence of a new, something we haven't met before. Once we've detected something, what action do we need to take to control the spread? What sort of planning do we need to be able to implement that action? And if we're talking about things like recurrent infections, what sort of vaccination strategies are needed in order to protect the population? Individual-based models I'm not going to talk about, but I'll just say that in those models you represent each host explicitly with all the sort of complexities. So very much like Marcel was talking about with the model for London. Very detailed observation of a particular population, and therefore the results that you get, if you've done it well, give you useful information about spread and control in that population, but they're not usually transportable to other scenarios, and you don't really know about which mechanisms are driving the dynamics. So in preference to individual-based models, I'm going to talk about using simple models, generic models, that will be robust to the sort of assumptions that you make, and I want to use those to explore population heterogeneity and structure within that, analytically if you can, and really to determine what the main drivers of the dynamics are. So I'll go back to the SIR model. This is a model that's been around for about 100 years, so it's not new. And you simply divide the population into 3 stages: those who are susceptible to the infection, those who are infected and infectious, and those who are removed. And this removed category is a bundle of all those who are not contributing to the spread or cannot contribute to the spread of the infection. So they may have been infected and recovered, they may have died, they may have been quarantined, but they're not playing any part in the spread of the transmission. Okay, and we'll think about just a closed population, and this is appropriate for so-called microparasites, that's viruses, bacteria, those sorts of things, not for macroparasites. Macroparasites are large, relatively larger, things like parasitic worms. They have part of the life cycle outside the host. The models are much, much more complicated. But for viruses and bacteria, where all the life cycle is inside the host, these models work. And then we can extend the models in the way that I'll outline a bit later. Okay, so basically the idea is that infections occur at a rate that depends on the numbers of susceptibles, X, and the number of infectives, Y, and their product, and that's what's called homogeneous mixing. So it just gives you the probability of an infection in each small time interval. Recoveries occur at a rate gamma per capita, per infected. So constant rate, for the statisticians that's exponential infectious periods, independent between individuals as you might expect. And it used to be thought, a common mistake used to be to think that if you used a deterministic model in this setup, you were getting the mean of the stochastic process, and that's not true. So these are about the only two equations I'm going to put up. If you look at the red one, that's just telling you that the rate of change of infectives, the infective number goes up with infections, decreases due to recoveries, and you just get that simple red equation there. If you write down the corresponding equation for the mean of the stochastic model, you get the equation above. And if you look carefully, you'll see that they're almost the same, except that the stochastic ones got this extra covariance term. Excuse me. The covariance will generally, well, at least initially, when everybody's either an X or a Y, and we haven't got to the stage when anybody is recovered or removed, that X plus Y is going to be N. That tells you that the covariance is negative, and that means that this last term is slowing up the rate of increase. So the mean of the stochastic process is increasing initially more slowly than the deterministic curve. Okay, that's just a little side thing for the moment. Now, if we want, starting from an initial position, if we want the number of infectives to increase, the sort of traditional epidemic where it goes up and then it comes down again, we want the thing in the curly brackets there in the red equation to be positive. Okay, so that the rate of change of Y is positive. And that, looking at it for t equals 0, gives you a threshold. It says that the proportion of susceptibles, if I can use this thing, this proportion here has got to be greater than this quantity gamma over lambda. Lambda over gamma, turning it up the other way, is what's called the reproduction ratio. That's a very crucial quantity, but a very simple quantity. It's simply, for a single infective, it's the mean number of individuals that that person will infect during their infectious period if all their contacts are with susceptible. So it's one infective, wholly susceptible population. How many do you infect? And that's this reproduction ratio. Okay, so it's fairly obvious if that number is less than 1, so each infective isn't even reproducing themselves, then you're not going to get an epidemic. If R0 is less than 1, 1 over R0 is greater than 1, proportions are never greater than 1, and that threshold never comes into play. We never get an outbreak. If R0, on the other hand, is greater than 1, so each individual is more than reproducing themselves, then you're going to get an outbreak. If R0 is greater than 1, 1 over R0 is less than 1, and as long as the number of susceptibles is big enough, it can exceed that proportion. Okay, so that all seems to make good sense. So that means it gives us a clue as to what we do to control the outbreak. We can either, basically we want to make R0 small. The smaller the R0, the less of an outbreak we get. So we make R0 small by increasing gamma, that's the recovery rate. Not quite clear how you do that, but what you can do is increase the quarantining rate. So effectively, you're getting them out of the way. So you can increase gamma, or you can decrease lambda, the infectiousness, which you do by some sort of biosecurity means. Make people wear face masks, wash their hands more, whatever it happens to be. If we've got an open population, then that tells us that as long as we can keep this proportion of susceptibles below this threshold, we won't get a major outbreak. So it's a very simple model. It's been around a long time, but it gives you very important practical insights. So as I'm going to show you in a minute, these deterministic models give you some sort of approximate large population behavior, but they don't tell you about things that we do care about. The chance that if you have a new infection that it becomes established, or about fade out of infection between outbreaks. If the population's small enough, you'll get a complete fade out of infection in the population between outbreaks, and you only get another outbreak if you get new infectives coming in to infect your susceptibles. So for these sort of things, you need a stochastic model. And the stochastic model gives you a similar sort of threshold, but it's not quite the same. So if you have a single infective, large population, everybody else is susceptible, then if R0's less than or equal to 1, you're certain that the outbreak will go extinct, the infection will go extinct, just like the deterministic case. But if you're R0's greater than 1, you're not certain anymore to get a big outbreak. You are in the deterministic analysis, but not in the stochastic one. So you get an outbreak with a probability 1 minus the 1 over R0, which is there for the probability of extinction. So that probability of a big outbreak is going to increase as R0 increases. So it all makes perfect sense. But you get this much more smooth evolution. So now we've got a condition for the probability of an outbreak. If we condition on that happening, so we're saying, okay, we've got an outbreak, now what? So if there's a major outbreak, then what you get is a sort of central limit type result. You end up with a Gaussian diffusion process, and the mean of that diffusion is the deterministic curve. So actually, this deterministic solution is a mean, but it's a conditional mean rather than the sort of unconditional one. But that's the link anyway. And it's important, this distinction at times. If we think about solving these models in terms of sets of ordinary differential equations, the variables are densities, and the fact that in a finite population, the proportion is actually not a continuous variable. It's treated as a continuous variable, but obviously it's really discrete. But we ignore that. And there are pitfalls in that. And there's a nice paper where he explains this by Dennis Mollison, who talks about the Atto fox. And the idea here was that if it's deterministic in that model, that variable never actually hits 0. It can get very, very small. We can get down to 10 to the minus 18, that is an Atto fox, 10 to the minus 18 of a rabid fox, but it would never actually 0. And if you've got that tiny little bit of a rabid fox lurking around, as you get more susceptibles coming in, it can start off a new wave of infection. So in the deterministic case, you will get repeated waves of infections spreading out across Western Europe, this was. Whereas in the stochastic case, you may get some new infection, some new wave, but eventually you know it's going to go to 0 and it will stop. So and the process will die out. So it's quite a big and important difference. Okay, so that was a very simple model. We can complicate it and do similar things. So we can put in all these things: demography, age structure, heterogeneity of the host and of the pathogen. I'm going to say something about heterogeneity of mixing, that is population structure and networks, but there are other things that we could do. So the things that we're interested in invasion. Does the infection get established in the population? Does it stay there once it's got in? What are the threshold behaviours that correspond to that simple model? We want to know about things like time to extinction and what's called the quasi-stationary equilibrium. That is, for some infections, TB for example, in a stochastic model you know eventually it's going to go extinct, but it can stay pottering on for very, very long periods of time in an apparent equilibrium, and that's called the quasi-stationary equilibrium. It's the equilibrium that applies and that occurs conditional on not having gone extinct yet. Okay, final size distribution. The final size is the total number that are infected. A lot of the theoretical results are asymptotic, that is, applying for large populations. But populations aren't always large, and so we'd like to know what the differences are when n is finite. And we're also sometimes interested in things like, we've had a major flu outbreak, we'd like to know what's the position now? People have got some residual immunity. It's not like starting off from the beginning. We want to know conditionally on having had a major outbreak already, what's going to happen next. Okay, so how do we get away from this homogeneous mixing, this XY rate of infection? Well, one route is the so-called metapopulations. Now in there, what you do is you divide the population into types or groups. So you can think of these as households or schools or cities, depending on what the context is. So in the IF group or type, you imagine that those individuals make contact with a rate that's type dependent, and then you have a matrix of probabilities which says what's the probability that a type A person is going to make contact with a type J person. That gives you a matrix. Now, the reproduction ratio, if you remember, was the mean number of susceptibles that would be infected by a single infective during their infectious period. Now we've got to make that a bit more complicated. We've got to look at that for each type I infective and say how many type J susceptibles is that person going to infect on average. So rather than just having one mean, we now have a whole matrix of means of numbers in the next generation. And the reproduction ratio, the important thing, the threshold quantity, turns out to be what's called the spectral radius or the dominant eigenvalue of that first generation matrix. So that just carries over in a fairly natural way. It took a bit of proving by the person who originally worked it all out. But it is quite a straightforward idea. So if, for example, we had households, so we've got a lot of little households and they're connected together in some way. So the households mix between them and people mix at a higher rate within the household. Okay? The effective R0 turns out to be what you would get if you forgot about them being households and just thought about them as single units, worked out your reproduction ratio for that population of households, and then amplified it by the mean size of an epidemic within one of your households. So you get a very simple result there. And it means that even if there's not a lot of mixing between the households, if the size of the epidemic within a household is big enough, that can inflate you and get you over the threshold unit value. Okay, that's a simple result, and obviously there's a lot of theory which is complicated. They made it more general, more realistic, if you like. The groups don't have to form partition of the population, they can overlap. You can have not only households or schools or whatever, but you could put in age structure as well, so that for many infections, young people or old people are going to progress at a different rate from the sort of main body of the population. You can put in groups on a network and do similar things there. If I go back to the one that I was talking about a minute ago, where you just have households mixing within the household and then at a lower rate between the households, then you can work out what the optimal vaccination strategy is. And the idea is that you have to reduce the level of susceptibility in the households to make them as equal as possible. So if you've only got a finite amount of vaccine available, you go in and you pick out the household with the highest number of susceptibles first, and you start vaccinating that, and you gradually work across all the households, bringing them down to some level, common level. Now, clearly totally impractical, and you wouldn't do it, but that is the optimal strategy in that context, and you can work out slightly more useful strategies. But it's useful to know what the optimal is, even if it's not going to be something that's attainable. Now, in a metapopulation, everybody mixes with everybody else, albeit at different rates. On a network model, of course, you only mix with those to whom you're connected, to whom you're neighbours on the network. And so what we want to know then is what properties of the graph are most responsible for driving the dynamics. Could be the node degree, the correlation of the degrees, the degree of clustering, that is the triangulation, the amount of triangulation of the network, the spectrum of the adjacency matrix, which gives you the structure of the network. What we want is to know what is the effect of this structure on those thresholds. How do we generalize those simple results? Quickly, I can't say much about models for networks, but basically node degree, number of edges that are emanating from a node, so the number of other nodes to which your target node is connected. So one route for modeling a network is to say we'll give each node a random degree. So that gives them, if you like, a number of little what are called stubs or arms from each node, and then we just join those up at random. And that's the so-called configuration graph. And a lot of work is done with that. The Edos-Renyi graph is a special case with Poisson degrees. There are models, preferential attachment models, which generate the way in which new nodes attach to an existing network, and they tend to prefer to attach to nodes with high degree. That gives you a power law tail. But the trouble is, these models are well understood, but the node degrees are uncorrelated and the graphs are unclustered. That is, the proportion of triangles goes to 0. Social networks aren't like that. So that's a problem. There are some alternatives. The so-called random geometric graph is one which has Poisson degrees but is clustered and is correlated. Another alternative is start with our simple configuration graph. So each node has got its own degree, and then we rewire it. We remove some edges and replace them with others, keeping the node degrees the same, putting in either correlation or clustering. And that's one way of getting something you can work with. So what we want to know is, for our network model, what are the threshold equivalents of R naught? What is the final size distribution, probability of a large outbreak, all those sort of things. We want to know how those quantities depend on the network topology. For example, and it matters, so this is an example, just to say the degree distribution matters. If we take a completely connected graph, that's your homogeneous mixing case where everybody's connected to everybody else, then there's a nice relationship, which I've given here, between the final size, which is Z infinity in this notation, and R naught to base that relationship. Now, if we take the configuration graph, so all we've done is change the degree distribution, otherwise we've still got lots of independence in there. R naught will depend on the degree variance. It's driven because it's to do with getting the thing started initially. It's to do with those high degree nodes. On the other hand, the final size is going to be it's at the other end of the outbreak, if you like, what determines the final size. And it's going to be to do with the sort of connectivity of odd nodes that aren't very well connected. So it's very sensitive to changes in low degree vertices. So we can see that just changing that degree distribution has had the effect of pulling apart this connection between R naught and final size. Yeah, okay, 2 more minutes, I think. So we know if we look at these random geometric graphs or the rewired configuration graphs where we've got correlation and clustering in there, we can find that there's very little effect of putting in the correlation. There's a lot of effect of putting in the clustering. So that really reduces transmission a lot. And if you look at the pictures of triangulated graphs, you can see why. At some level, a mathematical analysis requires some sort of underlying tree-like structure. And there is some work, which I've just described very briefly there, that shows this same sort of idea that clustering is the important thing in a rigorous analysis. What we'd like are models that blend local and global scales to get some sort of rather flexible but parsimonious network models. Something I've been looking at a bit is generalizing these random geometric graphs because they're analytically tractable, trying to get alternatives with different degrees of correlation and clustering. we want to be able to have weighted networks. We've heard a little bit about weighted networks earlier. We want them to evolve with time, and that means creation and annihilation of nodes as well as edges. Networks are sometimes caused by movement. One aspect is when you have onboard vehicle navigation systems, and viruses spread between computers if they're within a certain range. So then your network is continuously evolving as these vehicles move in and out of range and allow viruses to spread. And then, of course, the process, the evolution of the process, the dynamics of the infection, and the evolution of the network aren't necessarily independent. People will change their behavior when they see people around them getting infected. That means that they will change their behavior in terms of cutting their edges, their connections. We need approximation schemes. There are lots of heuristics, but we need to know when they work. We want to incorporate things like waning immunity. We need to know, for public health purposes, we need to know about parameter estimates early on. How do heterogeneities affect those? And then there's all the stuff to do with interventions. What's the effect of changing edge weight, changing topology, exploiting the topology by removing high degree nodes? All these things are ways of putting in interventions to control spread. So there are a lot of questions, a lot of things people are currently working on, but a lot still to do. And that's where I want to finish. Thank you.
Questions about it. The first one is that you mentioned, for example, the traffic data to find out how the network is in the society. But what kind of other data can you use for constructing the graph?
Well, what tends to happen is that either people use models, stochastic models for graphs of a bit the sort that I described, because then you know exactly what you're doing. You can, it's under your control. Or they go to the other extreme and they use real data. There are databases of networks, and they usually social networks that are used, and people try to use those. The problem with that is that then you don't really know. If you're trying to understand what the effect of structure is, having a model where you can control the structure and gradually increase the clustering is sort of slightly easier for a mathematician to cope with, at least, than taking a range of different examples of social networks that will have different amounts of clustering and trying to draw some conclusions from that. But both are done.
Yeah, and the second question is that have you think about to use when if the recovery stage then it's possible to reinfection by the same strains of the infection.
Yes, well, I didn't say anything about that, but again, that I just mentioned there's the issue of waning immunity. So, the simple SIR type case assumes that once you've been infected and recovered, you're not going to get reinfected again. But of course, in practice, especially for many things, you're not immune forever. So even if there's only one strain, you won't necessarily be immune forever. And if there are several strains, as there often are, then that makes it more complicated still. So again, there is work in that sort of area, but I think there are a lot of questions and issues to address there.
To identify the models, you have to use different data sources. I know, like for CJD, Spanish flu or swine flu, they essentially got the infection rate wrong. So the infection rate itself is absolutely critical. So what do they do? Do they go and do separate studies to get
I
key
think
parameters?
that, well, very often, depends whether you're doing it in real time.
Right.
And probably Ian would be better able to answer this than me, but if you're doing it in real time, they tend to, I mean, what you get from simple models is an exponential increase, and the rate of increase is related to the R0. So you're estimating that will give you R0, and then you've probably got some other data which would give you the infectious period, because you'll have some cases that you can hopefully know roughly when they were infected and when they recovered. So I think you tend to use those two bits of information, and that gets you back. Is that right? Oh, well, he's nodding, so hopefully it's roughly right. Or he's just being encouraged. That would get you back to the infection rate, which is the one that you tend not to know in advance. So I think usually it's coming from that initial exponential phase.
I mean, there's a sort of metaphorical point, a metaphysical point, that for these big models, you need to go to do different things to calibrate different parameters. I suppose that was what my point was.
Well, and you have to, I suppose that's what I was trying to indicate at the end, that there's this question of what you need straight away, right at the beginning, in order to be able to start taking steps to control it. And then you're going to have to sort of refine ideas later. I mean, as we did, thinking back to HIV in the end of the 80s, we had a whole range of different possibilities and gradually sort of narrowed down what was happening and what the parameters were. And of course, everything was time varying anyway, but even if we thought about fairly small amount of time, there was a lot of uncertainty to start with, and then as more data come in, you began to be able to eliminate some possibilities and pin down other bits.
Okay, we're actually running out of time, so you'll have to take that question just after at drinks, because we'll need to
All right.
swap over.
I'll see you at drinks time.
Yes, let's thank Valerie again.